This session will be by Dr. Susanne Renner, who really is a giant in botany and has done so much work in helping us to understand biogeography, phylogenetics. She is currently at Washington University in St. Louis, and Dr. Renner will be talking to us about the Summer-Solstice-as-Phenology-Switch hypothesis.
Okay. Thank you very much. I believe we are like almost 15 minutes behind schedule, so I'll try and make up a little bit. So for the past 17 or almost 18 years now, I have been monitoring and documenting the peak fall color change in two maple trees in front of my house. Because I also photographed not just the peak, because you never know exactly when the peak occurs. So, around the peak. And what you see from glancing at these dates here is that it doesn't appear to have changed at all. This is not that there hasn't been any temperature warming here in St. Louis. This is the average temperature in November in St. Louis, and it's now like 1.5 degrees Fahrenheit above the 1900 to 2000 average. This is the November temperature. The overall year temperature has gone up even more. But correlations will only get us this far. And so what I will be focusing on in my 15 minutes here are experiments addressing on how we might predict senescence. And these experiments, initially, we started with focusing on spring. Here you see my former master's and doctoral student, Konstantin Sohner, with the cool shades here, engaged in experiments carried out in the Munich Botanical Garden. And the conceptual framework was that a botanical garden can be seen as a common garden, at least for trees, because many trees from the northern hemisphere are growing together here without any opportunity for sexual reproduction. So they will exhibit more or less the traits that they have evolved under their native climates. Most of our experiments focused on the spring, but then in 2017, we began also thinking about experiments addressing senescence. And these experiments involved just a few species of potted saplings, and the black styrofoam plates that are circled here in the red circle will become important shortly. So one of our experiments focused on the frost damage in the spring and what happens to plants when they experience such frost damage. So the treatment involved potted saplings of fagus and two other species. And these saplings, this is the control, okay? And they either received some warming in the spring, or the saplings were carried into a large freezer, and the first cohort of leaves was killed. And it then took them about 3 weeks to put out a second cohort of leaves. And we studied how this would affect the bud growth rate here, millimeters per day. This was the response variable. And so it appeared that the damaged the saplings whose leaves have been really killed caught up pretty fast to the control and the ones that had experienced some warming. And then what happened was that those saplings that had been warmed in the spring senesced their leaves or finished their bud set. Here, the bud set was the control, the response variable, finished their bud set much earlier than the control. And most interesting and unexpected was that the second cohort of leaves that had been put out, really did a good job photosynthesizing away, and bud growth rate continued the longest in those plants that had experienced the damage. And at the time, we focused here on the compensation that these plants appear to be, all three species appear to be doing. This then led to follow-up experiments where we focused on the effect of winter and spring warming, again using potted saplings, all year warming, or summer autumn warming. And the response variable is the difference in treatment, in effect between treated and control plants in bud set, again, bud growth millimeters per day, or leaf senescence. And what we found was that spring warming had considerably delayed bud set. Okay. Excuse me, I have to actually change something here. Okay, and not delayed advance. Sorry. Bud set was greatly advanced by like almost 8 days when the spring warming had occurred. And leaf senescence, there was here's leaf senescence. Also, leaf senescence was advanced also by something like 3 days. Interestingly, the fall warming had no effect on bud set. That makes sense because the buds were already set. So no, of course it had no effect, but it delayed leaf senescence hugely. You can see this here by something like 13 days. Okay, so these opposing effects of spring warming versus fall warming on bud growth and leaf senescence then raised many questions and led to further experiments. So spring warming and fall warming have opposite effects, as I just showed you. And so that raises the question, at what point do trees switch their reaction to air temperature from reacting to spring warming with a investment in growth and a speedier bud set and senescence to fall warming having the opposite effect. And so, of course, in the spring and summer warming have positive effects on cambial activity, root exudates, bud sets, and fruit. And then at some point, and we want to find out at which point, trees need to focus on preparing for winter and to recuperate whatever they can from the leaves that they are about to drop. And also, of course, they need to focus on the bud set. And this is so interesting. If one hasn't really studied, or if you haven't paid attention to when the buds are set, this is so early. Here's bud set in a beach in Munich, 15th July. And here's a witch hazel bud photographed in St. Louis on the 12th of June. I went out this morning to the same bud. It basically grew very, very little after 12th June this year. So bud set is really early. So this is the experiment that involves those styrofoam plates that I showed before. And so the experiment involved shading half a plant, yeah, by placing the styrofoam, here you see it from the top, so that a part of the plant was on the right of the styrofoam and a part was on the other side of the styrofoam. This created differences in the ability of these two halves to photosynthesize. Of course, there were also full shade plants, fully shaded plants, fully sun-exposed plants, and controls. And the response variable here, or what we measured, was the photosynthesis of the leaves, which was measured with chlorophyll fluorometry several times during the growth period. So here you see the effect on the plants. Here the styrofoam plate has been tilted so to take this photo, okay? Dramatic difference between the shaded and non-shaded halves of the plants. And what you expect, of course, is that the fully sun-exposed plants should be done with their bud set and done with starting their senescence earlier than the ones that are in the shade. And you would think that these half-shaded plants, that there would be a difference in the ability to photosynthesize and grow between the two halves. And what we found was that in the fully sun-exposed plants, of course, they had a higher net primary production, of course, and they had earlier leaf senescence by 13 days. Here it is, in beech, and by 8 days in spirea. Now, what we found for the comparison between half shaded and half sun exposed, there was no difference in the time when the leaves senesced. And so this shows that if leaf level photosynthesis were driving the response here, you would have seen a difference. This means that really what what affects senescence in this species, in the two species on which we did these experiments, is the integration, is the growth and the meristemal growth and the other internal factors, not leaf level photosynthesis. We did further experiments in this paper that there is no time to go into here. So this then raised the question, what is the time when the response of plants switches? What is the precise time? And we used to address this, we used monitoring data from the past 60 years, 1951 to 2015, for 12,700 trees at 3,800 sites in Europe that have daily air temperature, irradiance, precipitation, and soil moisture. What they do not have is measurements of bud size. So we could not use bud set as the response variable. We had to go back to net primary production. So what we found was, using a sliding window approach, that the relative advancing versus delaying effects of net primary production on leaf shedding in these 12,700 trees. And leaf shedding, I should say, was defined as 50% leaves dropped, because these species don't have that color change that we have in the maples. Anyway, so the time, the model that best predicts the leaf shedding in these four species, the switch time was around the summer solstice. And we repeated this analysis for 10 species at the Harvard Forest, for which there are 30 years of data. Okay, so the summer solstice appears to be the point at which trees switch from growth to preparing for winter. Now, this was, as I said, from observational data, not from experiments. So clearly we wanted to do experiments now to investigate whether this is really true. And so these experiments are constitute a part of the doctoral dissertation of Dominic Rebindine, whom you see here, and I think he is in the audience. Dominic was also a co-author on our first paper, where we put forward the summer solstice hypothesis, the paper that I just described, basically. And I will now have just 2 slides showing some of the most exciting results from Dominic's doctoral research, advised by Konstantin Zoner, who now has his own lab at the ETH in Zurich, and with collaboration with Thomas Crowther, who is also there. Okay, so as shown in this wonderful paper here by Zweifel et al., trees grow at night. They didn't show it for the first time, but it's the best paper available at this time. For 7 species, here is the time of day with maximum growth, here growth per hour. And this is time of day maximum growth, annual radial growth in millimeters. And in this 7 species, the time of day when trees really grow is at night. This is 1 o'clock in the morning, 2 o'clock, 4 o'clock, 6 o'clock. This is when they get going. And this makes perfect sense, because that's the time of day when the water deficit will be lowest. So given this knowledge, what Dominic did was, in one of his experiments, he used 180 potted beech saplings. These are pretty large saplings. And he gave them the following treatments just before the summer solstice, okay, just before June 21st and just after June 21st. And what he did was, he either gave them a cooling, and it's pretty strong cooling, okay? Cooling during the day and cooling through, here's either full day cooling, night cooling, and not during the day, or day cooling. Here are these. This was applied before the solstice, and then it was applied to other saplings after the solstice. A really drastic treatment. And what he found was that those saplings that experienced the pre-solstice cooling from end of May until 21st of June, as you would expect, such strong cooling either during the entire day or during the daylight, the day, this is 24 hours, this is day, and this is night, strongly delayed, or night cooling strongly delayed bud set by 5 days, or bud growth rate by 5 days. And this makes sense because trees grow at night. If you cool it down, you slow the metabolism, you slow the growth. It's completely expected. But what happens if you apply these treatments after the summer solstice? This was wonderful. So after the summer solstice, 22 June to 21 July, the same treatments had this effect. If you cool these at night, you get 5-day slowing in the tree growth, in the bud growth. But if you cool them during the day, you have an advancement. So trees become sensitive to the cooling and they speed up their bud growth. This is so wonderful. They kind of know, okay, I better get going. I better finish my bud growth really fast. This is a wonderful illustration of how plants switch their behavior from receiving the same temperature treatment before or after the summer solstice. This is a wonderful experimental support for the summer solstice as a switch point in how plants react to temperature and to ultimately also to climate change. So this is my last slide. So in our first paper that I described, we also had a projection of tree response. Again, this was the monitored trees, 4 species of common European trees, of how they would behave until the year 2100. And so we all expect, as expected, they should continue to advance growth in the spring. And according to our monitoring data and understanding of what happens and how trees respond, they should change their fall senescence fairly in a fairly limited way. This is super important for when we model carbon uptake in northern temperate forests. And I could kick myself that I did not document leaf out in these same maple trees, which I could have done so easily to see whether there is really a correlation between what a plant does during the spring and what it does in the fall, that same plant individual. And this is because I failed to consider, until about 4 years ago, I failed to consider plants as individuals that are completely integrated systems that are super fine-tuned in their response over time and over years. They are just the most amazing and fine-tuned metabolic systems. Thank you very much.
Wonderful. Thank you so much, Dr. Renner. Our break is supposed to start now. I might suggest that we take one question for all 3 of our speakers and then give everyone a little bit of a break before the next session begins. There are a number of questions in the chat. So Dr. Inoue has been responding, but Drs. Zettelmoyer and Renner, you may want to look at the chat. So I'm just picking out one question that everyone could apply to all of your systems. And that question is, what recommendations do you have for land managers to implement the findings of your research to their land management practices and decisions? So any one of you 3 is welcome to chime in.
Well, I think the idea that was brought up earlier today about assisted migration could be an important one in terms of helping plants remain in the climate zone in which they're doing best. And unfortunately, some plants have seeds that don't disperse very far, especially up mountainsides. So it could be that assisted migration would be a good thing to do there.
Dr. Zettelmoyer or Renner, do you have any thoughts?
Some of the results that, particularly Dr. Inoue and I are highlighting was if we can think about these shifting phenology and responsive snowmelt effects on pollinators, that might lead to some avenues for increasing floral resources or considering nectar quality and quantity and that sort of thing, and managing pollinator populations, which would then feed back to affect the plants. But yeah, in our case, it's like a step away from that question at this point in time.